In the last session, we saw some toy problems. So now we will talk about some real world problems. So the first problem we will see is airline travel problem. So obviously the customer is going to call and then you have to book the flights, etc. So what is the state here? Each state includes a location, the current time, uh, then so the flight segment which needs to be booked, the status, etc. So also there's some extra information here. This is actually a real world problem which is a little more complex than the problems we have seen earlier basically. So what is the initial state is whatever the query is of the user. So the user will say I want to book from this place to this place on this date, etc. So those things will be the initial state, and the action to be taken is to take any flight from current location in any seat class, leaving after the current time, leaving enough time for within airport transfer, etc. So all these things have to be taken into account to find the action. And transition model will be to find the next destination from which you may have to book another flight. Goal test is are we at the final destination? And path cost is very complicated here, not like in the case of the things we saw earlier. Of course, monetary cost, waiting time, flight time, customs immigration procedures, seat quality, time of day, type of airlines, frequent flyer mileage awards, etc. So all these things will be taken into account for the path cost, and then you try to find something with the minimum path cost. And a good system also includes contingency plans basically. Okay. So this is one real world problem. Another real world problem is a touring problem. So it's something like the route finding or the traveling salesman problem. So visit every city once, starting and ending in Bucharest. So that is yeah, so if we take this map here, there are 20 cities here. So suppose you want to start from Bucharest and you want to go to every city once and then come back to Bucharest. So what is the best way of doing this? So that is what we generally call the traveling salesman problem basically. Okay. So obviously the state space, each state must include the current location and also the set of cities the agent has already visited. So initial state will be in Bucharest and visited Bucharest. So you will have visited, which will give the list of cities that he has already visited. Or in Vaslui visited Bucharest, etc. Okay. So this would be the state, and once you have this state, then what is the next city? So you have to take the action here, which will add one more city to the visited, and he'll be in that particular place. And the goal test is to see that all 20 cities have been visited, and of course you need to check the path cost. So which is the one which gives the lowest path cost? So the path cost would be the total distance that has been covered by the agent. Then we come to the traveling salesman problem. So this is akin to whatever we just saw. Okay. And we know that it is a NP hard problem. And there are other algorithms in the same way, such as planning the movement of automatic circuit board drills and stocking machines on shop floors, etc. So this is one problem. So the first one was the airlines problem, and then we have the traveling salesman problem. Automatic assembly sequencing. So if you have a number of different parts of say a particular motor or electric motor or some other system, how do you assemble them together? Okay, so there has to be a particular order in which you do this. You can't assemble part of it and then find that some small part should have gone inside when it hasn't been, and you need to open the whole thing out and redo it, etc. Okay, so things like assembly sequencing is one important real world problem. Okay. Um, so it could be even more difficult. For example, you could have like something like a geometrical problem, okay, like robot navigation, etc. So it should be checked also for feasibility. Okay, it should not be going against some blocked place or things of that sort. Um, and of course, if you take real world problems, especially things like robot navigation, etc., it's not for it to be practical. You should see that you don't have to explore the entire state space, but only part of the state space. And then protein design, in which the goal is to find a sequence of amino acids that will fold into a three-dimensional protein with the right properties to cure some disease. So it has to try out different sequences of amino acids to find which is the one which cures the disease that you want. So once you find such a thing, that will be your goal state basically. So these are some real world problems we are talking about. So how do we find the solution? So now we have seen how to formulate the problem. So once we formulate the problem, how do we actually solve that problem? Okay, so what we need to do is to find an action sequence, like we said. Okay, so you have to start at the initial state, and from the initial state, you have you can have a search tree. Okay, so the search tree from the initial state will show all the branches that it can take. Okay, so the actions that are possible for from that initial state leading to other states. Okay, and from those states you can again have branches going out which will show actions which can be taken from that point leading to other states basically. Okay, so this will form what is known as a search tree. Okay, now how we form the search tree is what we need to basically see, and the search tree you may not have to find the complete search tree. Maybe you can just even find the partial search tree. So obviously we start from the root node. Okay, so from the root node you have to see what are all the actions that are possible from that root node, right? And then expand that node. So let us see in this particular case. So we saw here you have this 20 cities here. So suppose I start from Arid, okay, and I want to go from there to say Bucharest. So what is the best route for me to take from Arid to Bucharest? So from Arid you can see that what are the actions that are possible. Okay, so we see that there are 3 outgoing links from here. Okay, so it's possible to go from Arid to Sibiu, from Arid to Zerent, and Arid to Timisoara. Okay, so there are 3 possible actions that can be taken. So you are going to get in this way. So you are starting from Arid, and so first you are going to start your search with just this particular node. Okay, and then this node is chosen for expansion, and when you choose this for expansion, you are going to get 3 nodes like this. Okay, so these are the 3 nodes that you are going to get from there. So if you can see, this is it is shaded, which means that this is a expanded node. So once a node is expanded, you are not going to go back to that node. Okay, so once you have expanded and got these 3 nodes, one of these three nodes will have to be chosen now for expansion. So say you are choosing this, okay, so this one is CBU. So if we take that, okay, these are all the possible. So you have three possible. Yeah. So from here you can go to this place, or you can go to this place, or you can go to this place, or you can go back to arid. There are four possible routes from here. Okay. So you can see that when you expand CBU, you are going to get these four nodes. Okay. And you can see here that these nodes, okay, are the unexpanded nodes, and they are like the leaf nodes. So what is a leaf node? A leaf node is a node which doesn't have any children, right? It has only a parent, it doesn't have any children. So it is a leaf node in this partial tree which has been created, okay? So if you look at all these leaf nodes, one of these leaf nodes will have to be chosen for expansion at every point in time. And when we expand a node, for example, if we go from arid to CBU and go again to arid, it doesn't make any sense. So generally what is done is that you see if it is already an explored node, then you are not going to again go back to arid. So it will be just like going round and round, okay, which in a circle, which is not to be done, right? So this is not expanded, you will get only these three nodes. So if you look at this, if you consider all the leaf nodes together, this is what is called the frontier. Okay, so I can say that this part, if I take like this will form the frontier. And the frontier, one of the nodes in the frontier will have to be chosen for expansion next. So that's the basic idea. Okay, so what do you do? And whenever you take a node and expand it, the new node which comes, you check whether it is a goal state. So once you reach a goal state, it means that you have reached your final destination, so you can stop at that particular point in time. You expand the current state to generate a new set of states. Okay, and the set of leaf nodes is called the frontier. Okay. So like they say in this particular case, these nodes which are in bold, okay, not shaded, forms the frontier, and one of these nodes will have to be chosen for expansion basically. So yeah, so if you go back to the same node again, it will give redundant paths. Okay, for example, if we say that let's go back to the, yeah. So suppose we say we are going from arid to CBU. If there is a direct route from here to here, okay, and there's also a route which goes from here and comes to CBU. But once we have reached this point once, okay, then there is no need to have another alternate route going to the same point, okay, because the first route has a direct straight path from arid to CBU. So this is the reason that a node which has already been explored will not be explored again. Okay, so let us look at the algorithm which is given here. Okay, yeah, so this is the tree search algorithm. So what you are doing basically is the initial state is put into frontier, because that is the leaf node which is there for expansion. There is no other node. Okay, if the frontier is empty, then return failure. Okay, so this happens when you are not able to find any path from your initial state to your goal state. It's possible that there is no road connecting the two places, right? In which case you'll get a failure. Otherwise you choose one leaf node. Okay, so at the beginning only the initial point node is there, so you have to choose that to expand. Okay, so you remove it from frontier. if the node contains a goal state, so what you do is you check if it is your goal state. Okay, so if it is your goal state, then you return the path from the goal state to the start state, or from the start state to the goal state. Otherwise, you expand the chosen node, okay, adding the resulting node to frontier. Okay, so this is the tree search. Okay, but now, like I said, there may be already nodes which have been explored, so no point in exploring those again. So that is what is called the graph search here. Okay, so you are initialize the explored set to be empty. So you are using the explored set over here. Choose a leaf node, remove it from frontier. If it contains a goal state, return the solution. Add the node to the explored set. So as soon as you take a node and use it for expansion, you add it to the explored set. Okay, then you expand the chosen node. Okay, adding the resultant node to the frontier. Okay, so you add it to the frontier only if it is not already in the frontier or the explored set. Okay, so this is the extra thing which is added here as compared to the tree search over here. So the tree search will result in a lot of redundant nodes and the same node occurring again and again, whereas graph search will get rid of nodes which have already been expanded and not go back to that, right? Okay, so the frontier separates the state space into the explored region and the unexplored region. Okay, so let us see what they mean by that. Yeah, so here we can see that suppose this is the explored node. Okay, so this is your frontier. Okay, so you can see that beyond the frontier you have the unexplored nodes. Then once you move from here and explore this node, you find all these nodes are coming into the frontier. So you can see that the frontier actually separates the unexplored nodes from the explored nodes basically. Okay. So because you're going to check whether something has already been explored and you're not going to explore it again, what you find is that sometimes some nodes will not have any children at all. Okay, so that no more expansion is required of that node. For example, taking this node. Okay, maybe this node has already been explored. So you are not going to expand this node any further. Okay, so basically what you are doing here is that you start with a single node, okay, which is the root node, and you are going to expand those nodes, okay, and finally you are going to come up with a tree like this, right, which will consist of nodes which have been expanded and the frontier nodes, okay, which need to be expanded. So what you need to see basically here is that the nodes, the order in which you expand these nodes will show the different search strategies which are there. Okay, so you may have different strategies. Different strategies will explore these nodes in a different order. Okay, and it may be that one order is better than the other order for a particular problem. Okay, for example, suppose you are going this way and you are going to, for example, if you go down, if you take these red nodes and you are exploring these, right, and you are coming here, if you had a solution somewhere here, this would have been a good strategy. But at the same time, if the node which you are searching for is somewhere here, right, then this is not a good strategy, because then you have to come back and then you have to go explore this, then you go explore this, etc. So the way in which the nodes are expanded will give the different search strategies that we have. Okay. So what I wanted to actually show you is, for example, if we take the 8 puzzle in this way, okay, so maybe I have like 4, 2, 6, 8, 1, 3, 5, 7. Okay, this may be your starting state, and maybe this is, you have another goal state here. Okay, maybe 1, 2, 3, 4, 5, 6, 7, 8. Okay, maybe this is your final state. So now what you can do, see from here is what are the actions that are possible. So you can move this blank this way, you can move the blank this way, you can move the blank up or you can move it down. So you are going to get 4 different strategies here. Okay. So if I say that okay, I am going to move the blank this way, you are going to get 4, 2, 6, 7, 8, 1, 3, 5. Okay. And if you are going to move the thing to the top, you are going to get 4, 6, 7, 2, 8, 1, 3, 5. Okay. In this way you will get a number of states, and from these states you can get other states. Obviously you are not going to move this blank back here because you are going to get an explored node, right. So if you keep doing this till you find a configuration which is equal to this configuration here, okay, at that time you stop. Okay. Now another thing that is done is to actually evaluate this. Okay. You say how close this is to this. Okay. Maybe you can say see how many of them are the same. Okay. So for example 2 and 2 are the same, right. So you can see how close this is to this. So let's just say that for the present, right. So depending on that we can evaluate each of these configurations and then choose the configuration which is got a better evaluation to expand, right. So that will lead to different ways of actually expanding this. Okay. So let us see yeah, so we can see there are different search strategies which you can use basically over here, right. We have the uninformed search or the blind search. So here you are not using any information regarding the particular problem which you have, right. You are just expanding it in some particular way, okay, that's all, in a very what do you say, random way. You are not using any information about maybe in some systematic way you are going to expand. When you have the informed or heuristic search, you are going to use some heuristics of the particular problem that you have. So in other words, maybe like trying to see how close that configuration is to your goal state, etc. Right. So if there's some heuristic that you can find, you can use that heuristic to see which node to expand first. And thirdly, we'll talk about game playing search where two people play, right. So when you are searching for a solution, you can see what you have done, but you don't know what the other person is going to do. Okay, so that makes it a little more complicated. So that's where the game playing search is used. Then we'll also talk about some randomized search algorithms like hill climbing, genetic algorithms, etc. Okay, so another thing we need to see is the performance of the problem solving. Okay, so okay, you have a strategy, you are going to get a solution, whatever, right. But how do we evaluate that solution that we have? Okay, so there are 4 criteria you have to use. One is the completeness. So completeness is it guaranteed to find a solution? Okay, so suppose there is a solution but it's not able to find that solution, right, which means it is not complete. Second is optimality. Does it give you the optimal solution, right? You have some criteria for optimality. Does it give you the solution which is optimal? Then you need to see things like time complexity and space complexity. How long does it take to find a solution? So because we will see when we go to some of the strategies that it takes so long that you can't use that algorithm in a practical way, right. So time complexity is very important. And in some cases, space complexity is very important, okay, because you find that some exponential strategies, if your problem is really big, it maybe the storage you require may go into things like petabytes, etc., which makes it very difficult to use, okay. So the time and space complexity are very important for big problems basically, okay. And what you can do is you can use things like a partial graph, okay. Try to see if there are some strategies where you try to find the goal, but you may not be expanding the entire search tree, but maybe only part of your search tree, okay. So how is the complexity expressed in terms of B? So B is the branching factor. So when you have a node and you're expanding, okay, B is the number of branches that you have. So if you have 3 branches, B will be equal to 3, right? So it's the maximum number of successors of a node, and D is the depth of the shallowest goal node. Okay, so till which depth should you go to find your goal node? Okay, so that is, all these things are considered. So when you use these, what you are going to get is how many nodes do you have to expand before you get a solution, okay. So time is measured in terms of number of nodes generated, and space is measured in terms of maximum number of nodes which you need to store in the memory, right. So maybe you go along one branch, and when you don't get the solution, you have to backtrack and take another path in your tree. So you may have to store all that information in your memory. So how much do you have to store in your memory? So usually if you look at the search cost, there are two things you can take into account. One is the search cost and the path cost of the solution found, right? So the search cost is the amount of time taken by the search, and the solution cost is the total length of the path in kilometers in the case of the path finding algorithm, right. So these two together can be combined to give you the search cost, the path cost, okay, the cost of finding a route from there to there. Okay. So having done this much, we will now go into each of the strategies we spoke about, that is uninformed search, informed search, game playing, and randomized search algorithms, okay. So in the next session, we'll go into the uninformed search strategies. So we'll close this session here.